My name is Cody Dennett. I am a third-year PhD candidate in the Department of Nuclear Science and Engineering here at MIT. My undergraduate degree is in engineering physics, actually, and so it's a very broad program of study where you learn all of the basics that sort of define what you can do in different fields of engineering. I only teach one class at Cornell in nuclear engineering, and it wasn't until the fall of my senior year that I was finally able to take it. Some of the problems that professor posed to us all seem to come down to how do the materials that you use to build nuclear systems fail? How do you qualify them? This seemed like the biggest limitation for implementing new systems. And so that's really where my interest came from. So we are working on developing new diagnostics to monitor irradiated material performance. Materials, as they're bombarded with irradiation, will degrade and fail in ways that are very unique to activated systems, so irradiated systems. Normally the way that people test materials for these environments, like you need to test structural materials for an engineering application, is to expose them to some condition and then measure them afterwards. The problem with this kind of procedure is that it's slow. And so what we're trying to do is develop new diagnostics to do online measurements of material properties as they're changing in active irradiation environments. And by doing this, the goal is to sort of shorten the time scale in the materials development cycle. So in this way, maybe you can iterate much more quickly with alloying elements in a steel or different structural designs for layered materials or things like that. The technique that we use is something called transient grating spectroscopy. And what we do is it's a technique which relies on using several different lasers to induce an excitation in the material and then monitor how that material responds. What's been interesting is that as we talk to other material scientists, every time we tell someone new about what this technique has the capability of doing, they come up with their own application space. And so it's been really interesting for us to have conversations with other material scientists to see what sort of interesting phenomenon can we study using these methods to study dynamic material changes that aren't related to necessarily our field of specialization at all. The one thing that we're interested in looking at is low temperature phase change materials, which may sound mysterious, but these are the things that they use in writable and rewritable disks. These materials work by inducing a phase change from laser heating in the disk material. Those two phases have different reflectivities, which can be used to write binary information onto the disk. Now, how exactly that low temperature phase transition happens is very important to the efficiency and the quality of these disks. And so looking at that phase transition at low temperatures in great detail is something that we think we might be able to do with this technique.